Hello, my name is Scott Gerenser, and I am a senior software engineer with Wheatstone Corporation. Today, we are going to be talking about studio elasticity. Studio elasticity, from hardware to virtual to cloud. Why does elasticity matter? And what do we mean by that exactly? As the name implies, an elastic studio is a flexible studio that can be scaled and adapted for different uses. Co-locating studios into a regional area where you have one studio feeding many stations, sharing assets, repurposing studios, making use of cloud technologies, as well as new ways of interfacing with the studio, like using a virtual mixer rather than a physical piece of hardware. It can also mean spending less money up front, but being able to easily expand or rent services from a cloud service provider. When we talk about elasticity, we're talking about adaptability. Can your studio adapt to change, which really is the only constant today? So, how we got here. Over the past few years, we've seen several trends that stretch our studios both geographically and for practical purposes. AOIP, audio over IP, allowed us to move from fixed function hardware to a much more flexible platform that takes advantage of the scalability and adaptability of software. Standards like AES-67 allow for a greater interconnection between various pieces of equipment, and enterprise network technology continues to make the studio more scalable as well. Starting with audio over IP, AOIP, which has come to dominate the broadcast audio market as a means of transmitting high-quality, lossless digital audio around a studio. But then to that, we add a method of control running over those same IP links. This is an important component as it allows us to switch a source or turn on a mic on or off from anywhere in the studio. AOIP drivers let a Windows or Linux PC transmit audio directly over the network without any digital analog conversion steps or extra hardware, replacing the old paradigm of multiple expensive sound cards in every box. But this is really just the beginning of the kind of scalability that AOIP has introduced. We've scaled processing, mixers, and so much more for use all across the network. Here, for example, in this graphic is a 8x2 utility mixer that's found in an I/O blade. And there's one of these at every connection point in a WheatNet-IP audio network. They can be used to do online mixing of sounds, segue remotely between feeds, virtually overdub pan, and so on. More recently, we've been able to stretch the AOIP scalability across even greater distances with codec appliances like Switchblade for WheatNet-IP that make use of the Opus audio codec to transmit up to 24 channels of high-quality audio and logic control for full studio operation between sites, with the only interconnection being the public internet. And AOIP has also radically blurred the lines between hardware and software. At the right is a LXE console, Wheatstone's AOIP console, that has soft controls that you can reprogram much like you do on a software app. On the left is an app for that same console that's moved all of those hardware functions into a software application that can run on a normal PC, laptop, or even a tablet. So standards, how have these helped with scalability? We have standards like AES-67 that make it possible to transport audio between networks and devices such as a WheatNet-IP facility at the home studio and a Dante networked environment in a stadium or other venue, so we can easily move audio between the two. AES-67 is part of the SEMPTE suite of standards for taking television facilities into the next generation of an entirely IP-routed facility. Codecs make it possible to fit programming across IP links. And of course, we also have SIP, the Session Initiation Protocol, which is a signaling protocol for initiating sessions that include media and what audio codec will be used, what bit rate, so on and so forth. And we'll talk about that a little more later. So some of these standards are born out of our industry and neighboring industries with a specific need, which is the case for AES-67. But others come from the enterprise IT world, which is the case for SIP, for example. So speaking of enterprise IT, It's brought about many of our advances into the scalable studio. As enterprise IT matures, it tends to spread to other industries. In broadcasting, we've adopted a number of these technologies and customized them for our own purposes. Starting with virtual machines, VMs have been with us for a while, but they're still very useful, especially as PCs and servers get faster and more powerful. You get more and more benefit from consolidating applications and services from multiple physical machines to a single machine running multiple VMs. Containers have exploded in popularity in the IT realm over the past several years, and for good reason. They give a lot of the upsides of VMs, isolation, security, reproducibility of an environment, without some of the downsides. At a really basic level, containers can be thought of as very lightweight VMs, allowing for very efficient operation of many different services, all within a single machine or a small number of machines. Plus, they're tailor-made for running in the cloud, where running your own VM hypervisor may not be practical. And then there's SIP, the Session Initiation Protocol, which was borrowed from the world of telephony and voice over IP, and it allows you to initiate and terminate multimedia sessions. When two devices are made aware of each other via SIP, they're able to talk back and forth about bandwidth, whether the audio is stereo or mono, the type of codec used, and other essential pieces of information. This makes codec devices much more useful, allowing a codec from one brand to talk seamlessly to a completely different model from another brand, or even to a software or cloud-based endpoint. And of course, the cloud, bringing software services, VMs, onto a huge distributed cluster of servers provided and managed by a cloud service provider. Think Amazon AWS, Microsoft Azure, and Google Cloud. Being such a huge topic these days, we'll expand more on cloud in the next few slides. Computing trends in general. The trends that we're seeing is processor power going way up, more CPU power, cores, more memory, more disk. So you don't necessarily need a dedicated box anymore for, say, a codec. You might be able to get an existing, have a codec in an existing I/O device, and maybe it only occupies a very small portion of the CPU budget, where traditionally you needed that separate box because just doing that codec processing essentially would use up all of the CPU power in that device. More CPU power also allows you to do more things in software that used to be done in hardware, or a combination of hardware and software. Another trend is open source applications. For example, Opus is a completely free codec, and the quality is really very good. And general purpose CPU power is just so much higher today than it was. So we're getting away from the dedicated box and moving more into the software realm, all the way up to the cloud. Virtualization has been around for a while, but what makes it more practical today is with core counts going up, prices going down. This can allow for consolidation of, say, 10 servers down to only 1 or 2. 10 years ago, a 32-core machine might have been upwards of $100,000. Now you could buy a similar, actually a more powerful 32-core machine with hundreds of gigabytes of RAM for sometimes less than $10,000, maybe even close to $5,000. And as cloud becomes more prevalent, if your application isn't particularly latency sensitive, you might just prefer to let a cloud service provider handle the hardware and only rent the time that you need. You wouldn't even need to worry about buying any hardware. So, speaking of cloud, a recent survey by INAP indicated that the vast majority of IT professionals were looking to shift to cloud-based solutions in the next 3 years. Interestingly, a little over 2/3 of those were already hosting services in a private cloud. So, cloud computing. The very basic definition of cloud is that it's an internet-based computing whereby you have shared resources, software, and information. You'll hear terms like SaaS, software as a service, IaaS, PaaS. Pretty much all boils down to the practice of using a network of servers hosted on the internet to store, manage, and process data, rather than a local server or a personal computer. Usually we talk about the well-known public cloud service providers like Amazon AWS or Microsoft Azure, but you can actually set up a private cloud or even a hybrid of the two. So getting there. We talked earlier about virtualizing the hardware and mixing. When we start to move to VMs on a local server, we can then migrate the desktop environment in software, creating a small cloud. Automation companies are already centralizing automation on virtual machines. For example, Wheatstone's been experimenting with the Armed Forces Network and others who are consolidating a lot of services onto a small number of centrally located servers running on a number of virtual machines. We're seeing more and more of this with our automation partners because they can remove all the PCs in a studio along with all those noisy fans that use space and use that for something else, and partition automation functions to a virtualized file server in the TOC. Or maybe we don't even need a TOC. Maybe that server could be hosted at a cloud service provider. This is really making full use of the cloud. At this point, we'd be fully virtualized. But we're really not there yet as an industry. We're getting closer. But there's a couple of considerations that are important to keep in mind when moving any services from on-premise to a CSP, as we'll discuss in the next few slides. So a big one is latency. Latency is a fact of physics. In some cases, latency isn't an issue, such as for downloading a news show. But to produce in real time, it can be a big problem. Latency over the internet can be highly variable and change minute by minute depending on traffic and routing changes at the ISP level. But even best case latency is limited by physics, the speed of light. In a fiber optic cable, the realistic latency is about 0.82 milliseconds per 100 miles. So a 1,000-mile link will add a minimum of 8.2 milliseconds of latency. But realistically, once you add in routers and switches and other hardware, a 1,000-mile link is likely to add upwards of 50 milliseconds of latency. Then there's additional latency in the audio encode and decode process and latency caused by buffering. Realistically, in the field, we've actually seen latencies of 100 up to 400 milliseconds or more when transporting audio over several hundred miles. And then there's jitter. Jitter is the variance of packet flow from endpoint to endpoint. If we don't get packets at a regular interval, the buffers will starve and audio will break up. Latency doesn't cause this. We could theoretically have really large latency with zero jitter and things would play out just fine, just delayed. However, if latency is varying, we could have a problem, and we call this jitter. What might cause this? Well, one way is illustrated here. The internet uses a network to route traffic, and if one switch gets too busy or goes down, the traffic can be shunted to another switch, increasing the number of hops and changing the latency. Also, if any of these switches or networks get overloaded, they begin to queue packets, which also causes varying latency. And this can be catastrophic if the buffer sizes are not adjusted. Bottom line, reducing latency can be done to a point, but real-time applications often require a very low jitter network, which can be difficult to achieve over the internet. Reliability. Unlike a lot of enterprises, radio stations and television stations need to have almost 100% uptime. Here's a diagram showing the downtime of some of the most popular cloud providers in 2018. As you can see, Azure was down almost a day and a half in aggregate. And even the best, in this case Google Cloud, was down a little over 3 hours. What's not here is that when was the downtime? Was it all at once? Was it spaced out over time? Maybe you lose a few minutes here and there for a few days. That could be a serious problem for a broadcaster. So, in closing, AOIP and enterprise IT trends continue to converge to create opportunities for studio flexibility. More CPU power, core counts, and memory drive up the use of virtual software apps in place of dedicated hardware. And standards are leveraging all of that across distances and platforms. As that continues to happen, we as an industry can only benefit from the results as long as we're prepared for the changes. Thank you. And if you have any questions, please feel free to email me at scott.gerenser@wheatstone.com.